These are solutions to recitation activity 3. So first question, right? Balance the reaction for the combustion of butane with oxygen. I don't know if you'll see too much nomenclature where you have to know nomenclature in chapter 3 and beyond, like on a test where you'll be graded on remembering the formula of butane, but I think it's useful to remember that butane has the formula. It's the C4 hydrocarbon. The hydrogen count would be 10, CH3, CH2, CH2, CH3. Whether that's a gas or a liquid, let's write it as a liquid. You may not know the physical state of every substance. O2, of course, would be a gas at room temperature. Then we're going to have the combustion reaction produce CO2, gas, and then water. Could be a gas or a liquid depending on how we carry this reaction out. Not a big detail. I'm going to write it here as a gas. Imagine like butane's burning and the flame allows water to evaporate or just remain a gas following the reaction. So let's balance the carbons first. So 4 CO2 puts those into balance. 5 for water puts the hydrogens 10 on both sides into balance. But now I'm going to be at a fraction for O2 because I have 8 plus 5, so that's 13 O's on this side of the reaction. So that's going to need 13 halves O2, and generally we shouldn't have a fraction in our overall reaction. So how about I double my coefficients of all these reactions? So go to 2, 13, 8, and then 10. There's a quick double check would be 8 carbons on both sides, 20 and 20 hydrogens on both sides. 13 times 2 is 26. 16 and 10, 26. So 26 O's on both sides of the reaction. Second part here says, right, balance the reaction for the formation of aluminum oxide from aluminum and O2. Classify the type of reaction here. So we're producing aluminum oxide from the reaction of aluminum solid plus O2 gas. We're going to produce that common ionic compound, so Al3 plus, O2 minus, so we're going to get Al2O3 as the product in the reaction. So I'm just circling out the actual formula of the product. And then we have an odd count of O, even count of O, so let's go 2 here to give me an even number of oxygens, so that'll be 6 total O's, so 3 O2s puts oxygen into balance, and we need 4 in front of aluminum. And this, of course, would be an example of a combination reaction because we're combining our elements. If you flip the reaction, it would be a decomposition reaction, or anything you go from one reactant to 2 or more products would be a decomposition. What's the percent sodium in sodium carbonate given the formula here? So the percent sodium, I'm going to add this. This should say by mass, just to clearly be asking for the mass percentage. And so the percent by mass of CO2, that is sodium. We just look at the formula and see that there's 2 sodium. So I take 2 times the atomic weight of sodium on the periodic table. And so that is 22.99. And then divide by the formula weight. So again, I'm getting this from the periodic table for sodium. And then I divide that by the entire formula weight. So that'll be 2, do this on the side here, 2 times 22.99 plus 12.01 for carbon plus 16.00 times 3 for the oxygens. This gives me the formula weight for the compound is 105.99. So we're taking the fraction of mass, that's sodium, divided by the total mass of the whole formula. And so this will tell me that the percent by mass, that's sodium, should be 2 times 22.99 divided by the formula weight. This would be 43.4% to the nearest tenth of a percent. Question 3, to 4 sig figs, calculate the mass of a molecule of CO2 in atomic mass units. So the atomic mass unit masses, I can use the periodic table. So 1 molecule of CO2 should be the mass of carbon in AMU plus 2 times the mass of oxygen in AMU. So that'll be 44.01 AMU. To 3 sig figs is 44.0. Or sorry, it does say to 4 sig figs, so 44.01 34.01. Now, maybe it would have been wise to have included an extra sig figs to see if we would happen to round up or down off the 1 here, but this is good enough. If we're going to about 4 sig figs to most of our atomic weights, we'll work out for most of our problems in lecture. So what's the mass of 1 mole of CO2 in grams? This is actually pretty easy too, because I can look at the periodic table and see that the molar mass of carbon is 12.01 grams per mole of carbon, and then plus 2 times 16.00 grams per mole of oxygen. So the molar mass, so 1 mole of CO2 should have a mass of 44.01 grams. Okay, now you can just know that the periodic table masses are interchangeable with the units, or you can just convert AMU to grams and then convert atoms to moles. So you multiply by Avogadro's number, then you divide by Avogadro's number. Now, if we want the mass of a single molecule of CO2, now this should be really, really small. This should be a really tiny mass just to see how much the number of grams will calculate. We can do 1 and 2. We can start with either the grams per mole or the AMU. Let me start with the AMU. I like the AMU mass because it tells me the mass of a single molecule is that number of AMU. Then I just say, I just have to use a conversion factor. Either I look it up, which you could, we'll give you this conversion factor if you need it on test, but it's just Avogadro's number. There's an Avogadro's number of AMU per 1 gram. Okay, and so we divide 44.01 by Avogadro's number. And again, might have been wise to include an extra digit on the Avogadro's number here, but we'll go good enough with 4. So that gives me 7.308 times 10 to the minus 23 grams. So obviously a really, really low mass for a single molecule in grams. Question 4, a mineral contains these percentages of copper, iron, and sulfur by mass. And so the mass percentages we can relate those to the mole-like percentages or fractions, and then we can relate those to hopefully a whole number ratio to get the formula. So the best we can do with percent by mass data is an empirical formula. So we can't get any kind of molecular formula from this data, but we can at least get the empirical formula. And so the way these problems generally begin is with a ratio of the masses that would be true for this information. So if I have 34.6 grams of copper, then the amount of iron that should be present should be in this ratio to 30.4 grams of iron and present to a ratio of 34.9 grams of sulfur. Now, these masses here, I'm converting the percentages into grams, but what I need to do is just use 3 masses here that are true for this information that's given. So if a sample is 34.6% copper, if I had a 100-gram sample, so a 100-gram sample would be 34.6 grams of copper, 30.4 grams of iron, etc., 34.9 grams of sulfur within that sample. So I can assume, a lot of times these problems start with assume 100 grams. You can assume whatever mass you want to assume. Just assume a mass that allows you to calculate a ratio of masses that is true for the given information. It's going to be a lot easier. You're not going to have to throw a calculator out. You're not going to have to use a calculator if you use a 100-gram sample and just convert the percentages to grams. But we just want to use ratios that we want to keep that mass ratio intact because I'm going to convert these into moles for each of those elements. So the molar mass of copper is 63.55. Per mole of copper. Iron has its molar mass is 55.85 grams per mole of iron. And then 1 mole of sulfur is 32.06 grams. There should be a 2 here, just making sure we see 32.06. Okay, and so let's go ahead and work out these number of moles. So 34.6 divide by 63.55 is 0.544. So that many moles of copper. And then I do 30.4 divide by 55.85. That's works out to be the same. That's good. That's helpful. I have a ratio of 1 to 1 here. At least let's get all of our numbers and start thinking of ratios again. So let me do the last one, 34.9, divide by 32.06, 1.089. 1.089. So the issue here is I've kept my ratios intact. I've just taken the mass ratios and converted them into mole ratios. And you can kind of see it looks like, I'll do the math in just a second, but it's looking like 1 to 1 to 2, like 1 part copper to 1 part iron to 2 parts sulfur. How can we see that for sure? Well, let's look for the smallest number. So of these numbers here, I'm just inspecting which of them is the smallest. And so 2 of them are the same, that also are the smallest. So let's divide them all by that same number. And I have to divide them all by the same number, otherwise I break the ratio. So I'm just trying to get a whole number ratio here is all I'm trying to do. And I think it's pretty obvious that we're going to get the final number. Yep, it does work out to be 2. So 1 mole, just going to 1 sig fig here is good. Because, well, let me also put this here, that you would be tracking these to still their full numbers. Obviously, the number by itself is 1.00. But then I get 2.00 moles of sulfur. So my formula would be Cu Fe S2 would be my empirical formula. Answer D. Now, a few things. One, you should be within a pretty close, within about 0.05 here to be able to round. If you get a number here that works out to be 2.25, we don't have a whole number. We need to then think, does doubling lead them all to be whole numbers? Nope, it would be tripling or quadrupling. So you start thinking, if these aren't whole numbers, you then start thinking, do I need to double them all, triple them all, quadruple them all, and find the smallest multiple to give you whole numbers to get you that empirical formula. If you use precise, usually where you run into issues is being a little bit imprecise with these weights. And in fact, I just noticed I inverted this conversion here when I wrote it. This should be 32.06 grams in the denominator, moles of sulfur in the numerator. So I just had inverted that. Okay, so percent by mass problems can get us an empirical formula. Only issue is we got to keep our mass ratio to our mole ratio intact, look for a whole number multiple that then gives us whole number ratios of the elements in the compound. Question 5 here is kind of like the second part example. Like once you determine an empirical formula, perhaps from the percent by mass data, let's say you determine an empirical formula for a compound as C3H4O, and then let's say we do an experiment, like mass spec is how we determine this in the lab, but that's one of the key experiments. Is like a mass spectrometry experiment can give us the molecular weight of a compound, and let's say we determine the molecular weight of a compound, of this compound is 336.4 AMU. What is the molecular formula? Well, we know its empirical formula C3H4O, so the empirical formula weight is a value we can calculate just by taking 3 times carbon's mass, so that's 3 times 12.01. We have 4 hydrogens, 4 times 1.008 plus 16.00 gives me 56.06 AMU. And so the issue is how many of these empirical units there are in that molecular formula. The molecular formula should simplify down to C3H4O. So maybe it's C6H8O2, maybe it's C9H12O3, etc. So the way we can figure this out, how many multiples there are, is to take the empirical weight, the molecular weight, the weight of the molecule, and divide it by the empirical weight. So take 336.4, divide it by 56.06, and I get 6. Now, again, you should be within You should get pretty close to a whole number here. And again, the issue is usually being precise with your atomic weights. If you use 12 and 1 for C and H, you might get a little bit of a rounding error as opposed to 12.01 and 1.008. But being a little bit precise here might be helpful in these types of problems. But so I have to take let me write this C3H4O out again here, the empirical formula, and we write a 1 in. I just need to multiply these all by 6. So I should get C18H24O6. Question 6 here. Two and a half moles of phosphorus, 10.0 moles of O2. React according to the reaction below. How many moles of P4O10 form when this reaction is complete? Now, one thing you may think is, well, let's add the two together. Take the one reactant plus the other, but that doesn't entirely work because we're combining these molecules together. Then we also have a limiting versus excess reactant problem here that we need to think about. So I can write this out. Sometimes this is helpful, sometimes it's not. Or sometimes this is useful for a problem, sometimes it's not. It kind of all depends. But before the reaction takes place, I have these many moles of my two reactants of P4 and the O2. And then initially, before the reaction takes place, I don't have any of the product. And so then we're either going to consume all of the O2 and convert that into as much P4O10 as possible, or consume all of the P4 and convert that into the maximum amount possible of P4O10. One of these could be left over if we run out of one of the reactants first. So one thing I might calculate is the number of moles of P4O10 that I would get if I consume all the oxygen. For every 5 moles of oxygen that reacts, I produce 1 mole of P4O10. So that would give me 2.00 moles of P4O10. So 2 moles are produced if I consume all the oxygen. So now this step here assumes that I have enough P4 for that reaction to take place. So as long as I have enough phosphorus in the form of P4 to produce the phosphorus into this compound, then this quantity of P4O10 can be produced. Okay, so now let me run through the problem consuming all of the given P4. So if I start with 2.5 moles of P4 and make as much product as possible. Whoops. So again, we're asking the question, how many moles of P4O10 can we produce? Whoops. So the number of moles of P4O10 is what we're looking for here, but starting with the 2.5 moles of P4, and for every 1 mole of P4 that's consumed, we produce 1 mole of P4O10. So that means I get 2.5 moles of the product. But to get to 2.5 moles of product, I need more oxygen than what I have available. I consume all the oxygen, I make 2 moles of my product, and then I'm out of oxygen. So my oxygen is gone once I get to 2 moles of the product, so I can never get to the 2.5 moles of product. So the most P4O10 I can produce by this reaction would be 2.0 moles. Now, if we complete our BCA chart, or kind of like include a few other details here that you may or may not need to include, but sometimes it's useful to see a second approach or to try to understand these charts. If I set up a BCA is one form, but before change, and then BCA after. There's an ice table later that you learn later, and I thought I was confusing it with the ice chart. But BCA before the reaction takes place, C is the change during the reaction or due to the reaction taking place, and A is what's present after. And so I can write this here, where X is just for every X of P4 that I lose. I'm just looking at the coefficient in front of here to write minus 1X. So I'm losing my reactant, so I'm writing minus. And then I'd be gaining the products. And so I'm just going in terms of the coefficients in the reaction. So for like every 1X of P4 that I lose, I'm going to lose 5X of O2 and produce X amount of P4O10. Okay, and so then one of these two should hit 0. This was kind of the problem we were just solving before by thinking of which of the reactants is fully consumed. One of those is going to hit 0, so that's kind of like our initial question is which one's completely consumed. Well, let's double check or kind of start with the idea that it should be O2 completely consumed. So 10.0 minus 5x is equal to 0. So you can solve that for x, right? That x is going to be equal to 2.00 moles in that case. And so then we're going to lose 2.00 moles and leave behind 0.5 moles of the P4 remain after the reaction completes. And then I'm going to produce 2.00 moles of the product. So you can calculate and try to consider, okay, what would X be if one of the reactants is completely consumed? If we go back to the problem and say, well, if we forget about the limiting reactant, if I try to set X equal to 0, or if I try to set the after for P4 to 0, then X is 2.5. If I said X be 2.5, then I would have a negative amount of oxygen left over after the reaction. We can't go negative. We have to stop at 0. So you can think through these problems with a BCA chart. You can think through them with some, dimensional analysis. Usually the dimensional analysis math is what most students choose to do to solve a problem like this, like on a test or quiz or on a homework. But the BCA chart is maybe the understanding of how it works. It's kind of the thought process that you might be doing when you kind of say, well, if all the oxygen is consumed with as much P4 that it takes to react with it, then I produce 2 moles of product. If 2.5 moles of P4 were to react with as much O2 as it takes to produce a product, I would get more product than what O2 allows me to produce. Question 7, how many grams of HCl are produced from this reaction here? 1.23 grams of TiCl4 with excess water. So we're reacting this, we're told, with an excess of water to produce TiO2 and HCl. How many grams of HCl are produced from the reaction of 1.23 grams of titanium chloride? So this could be a this could be a BCA chart. Like, I wouldn't necessarily think this is an easy problem to do BCA because I got to convert into moles here. So if I start plugging numbers in here, I want to go into moles. So I'd have to convert this to moles, plug it into the table. At least I'm told that I have an excess of O2. If I'm setting up the minus x, minus 2x, plus x, plus 4x, I can only see the x values and what's present after is, we could then, see that x and 4x are present after. We still have our excess of water, and then we have, none of the limiting reactant, titanium chloride. So we'd want to convert 1.23 grams to moles to plug into this chart here, and it would allow us to solve for x, and then we'd have 4 times x for HCl. If you're kind of like confused at everything I just said here, just know that the BCA chart is a thought-provoking table. It might help you understanding some of the details in the reaction. But let's just do this with dimensional analysis. So let's really solve this problem, plugging some numbers into a dimensional analysis series of conversions. So we're looking for the number of grams of HCl. Helpful if I can write the letter I'm saying. So HCl, number of grams of HCl. We start with our 1.23 grams of titanium chloride. Our conversions are, from the balanced reactions. For every 1 mole of TiCl4 that reacts, I produce 4 moles of HCl, so I have to go grams to mole. So I have to take titanium, 47.88 grams per mole, plus 35.45 times 4 for the 4 chlorines. So that's 189.7 grams per mole of TiCl4. And then for every 1 mole from the reaction, for every 1 mole of TiCl4, I produce 4 moles of HCl. And so these are coming from the coefficients in that balanced reaction. This is coming from the periodic table. And then we go back to the periodic table. 1 mole of HCl is 1.008 grams per mole hydrogen plus 35.45 for chlorine. So that's 36.46 grams. And so 1.23 divided by 189.7. I'm going to hit enter there. That's the moles you'd be entering here. It's like a small number. It makes the chart a little tricky to do for this particular example. So maybe we don't do a BCA chart, but maybe it helps us understand we're losing our reactants, gaining our products. Multiplied by 4, so 1 mole of TiCl4 to 4 moles of product times 36.46 grams per mole, so that's 0.946. Sig figs real quick, 3 sig figs. We had 4, that's good enough. These are exact numbers from counting, so we're not rounding to 1 sig fig from our coefficients. And then we, 4 digits on our conversion here. So we're just using enough digits on our molar masses for our molecules and not have to cause us to round from them. So we keep 3 digits here on our answer, 0.946 grams. Question 8 here. We have 2.5 moles of titanium chloride, 5 moles of water. So the same reaction as the previous page, but with some numbers thrown in. So with the moles already given to us, now this is probably an easier BCA chart. So the reaction is allowed to react to completion. Which reactant is the excess reactant? Well, this, I hope you see, gives you a pretty easy way to see the minus x, minus 2x. And again, that's minus 1x because there's a 1 in front of the titanium chloride for its coefficient, minus 2, minus because the reactants, and 2 for the 2 and for the water, plus x plus 4x here across the board. And so then which of these is 0? Well, imagine, just if you're not sure, just pick one to be 0. Like let's make this one 0. What's x equal to? X would be 2.5, because 5 minus 2 times 2.5 would be 0. So if this is true, then x is equal to 2.50 mole. And if x is 2.5 moles, do you see how we're getting a negative quantity in TiCl4? So what that means is that this isn't going to 0. The other one is going to go to 0. And so that's going to make x equal to 2.25 mole. And so then 5 moles minus 2 times 2.25 is equal to 0.50 moles. I'm not asked yet about the product, but let's go ahead and work those out. It's probably the second part that I haven't looked at yet, but I'm guessing, 0.50 moles are what we produce of TiO2, and then 4 times that, so 2.00 moles of HCl. So some problems, BCA chart, pretty easy to plug the numbers into. Usually if I'm given moles here, I think BCA chart, because it already gives me the numbers. If I'm given grams here, I probably think, well, I have to do conversions to get the molar masses and to convert to moles. So I'm just going to throw everything into dimensional analysis if I'm given masses as my usual kind of go-to problem solving step here. So TiCl4 in this example went to 0, so this is the limiting reactant. And then the excess reactant, the one left over, is water. So water is the excess reactant. How much of the excess reactant remains? Half a mole. Now, this information over here, we were technically not asked this information here. We could have either filled it in like we did here just to kind of complete the chart, or perhaps neglected it and not worried about it. Question 9, 2 moles of iron oxide, 6.5 moles of carbon react. What's the percent yield of the reaction if we get 3.64 moles of of iron to produce in the reaction? So again, I go back to a BCA chart. Now maybe let's maybe hand wave a BCA chart where I think you can if you get the BCA chart from the previous page, you can probably see carbons in excess, because I'm going to need 6 moles of carbon to react with 2 moles of the iron Fe2O3. I have 6.5, so I'm going to have a little bit of an excess of carbon here. So I'm pretty certain here that it's the Fe2O3 that's my limiting reactant. But let's pretend like maybe we didn't know that, or we weren't sure and wanted to do this some other way. Well, let's do this. Let's calculate the number of moles of iron you would get if you produce it from all of the available Fe2O3. This kind of goes back through the problem we were solving before. I forgot to write the mole in. I wrote that sloppy. Let me write this again. 2.00 mole Fe2O3. For every 1 mole, just in the coefficient of 1 in front of Fe2O3 in the reaction, I produce 2 moles of Fe. And we don't need to go to grams because we're still working in moles here, so that's fine. That would be 4.00 moles of iron. If you're not sure the limiting reactant problem, then we just need to do this step here. The moles of iron you get if you consume all of the carbon. This will help us identify the limiting reactant. For every 3 moles of carbon that react, we get 2 moles of iron that form. So 6.5 times 2 divided by 3 is a little bit over 4. It's 4.33 moles of iron. Okay, so now which of these is the actual yield that we expect for iron? And it's the lesser quantity. Why is it the lesser quantity? Well, when we hit 4 moles of iron, we've consumed all of the Fe2O3 and it's gone, and we've used as much carbon as it takes to produce that quantity. When we consume all the carbon, we see that we would have gotten more iron, but we would have ran out of the Fe2O3. So we can never get to the 4.33 moles. We have to stop for the yield of this reaction. So this value here is my theoretical yield. I sometimes call this the maximum possible yield, but our yield would be the actual yield, or percent yield anyways, would be the actual yield over the maximum possible that the stoichiometry would have allowed for, 4.00 moles, so that's going to be probably about 91%. There we go. All right, so that'll do it for this activity. Thank you for your attention.